now we see one interesting technique for balancing the midpoint voltage with the help of virtual space vector. Now, what is a virtual space vector? Virtual space vector is a space vector which is formed by using the normal space vectors, okay, but for different durations of time. For example, this vector, one example say of a virtual space vector is V z m 1. Okay. So, this is the vector here. This vector does not exist because we do not have any switching state which will produce this vector. Of course, we have switching states that produce this vector, this vector, this vector, this vector, this vector and this vector. So, these 1, 2, 3, 4, 5, 6, these 6 vectors we can produce because we have switching states for them. However, this vector cannot be produced directly like the switching state. So, this vector how can we produce? We can produce this vector by applying this vector and this vector for equal duration of time. Okay. If I apply this and this, these 3 vectors for equal duration of time, I will get to this vector which is at the centroid of the triangle. Okay. Similarly, if I apply this and this for equal duration of time, I will get this vector. Okay. So, therefore, this V z m 1 which is shown here is a virtual vector which is formed by switching 3 boundary vectors like this one and this one. These 3 vectors can be switched for equal duration of time so as to produce this virtual vector V z m 1 which lies at the centroid of the equilateral triangle. Utilizing this V z m 1, we will be making the midpoint voltage fluctuations minimum. Let us see how it works. So, remember that we had said that plus 0 minus or the medium vector or the middle vector was the problematic vector, okay, for the capacitor voltage balancing. So, this vector plus 0 minus, this vector will not be directly used, okay, and we will redefine how we define the vectors in the sector. So, that is why you see here we have not, so we have used these black circles for the vectors, but we have not used any black circle here. So, that means this vector we will not use in the conventional way, we will redefine how the vectors are. Okay. So, how do we redefine the new vectors in this sector? Okay. So, far, so we are now redefining how the vectors are. So, this redefinition of vector is given as like this. So, let us see what are these vectors. V z 0 is this vector which is switched with 0 0 0 combination, okay, plain and simple. Okay. We are not going to use, so in this strategy we are not going to use the plus 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 or minus minus minus. So, we are going to use the V z 0 0 0 and indicate the V z 0 here. Okay. Next, we have V z s 1, that is this small vector, okay, V z s 1. Now, V z s 1, what it means, how are we getting this vector? V z s 1 is formed by switching plus 0 0 and 0 minus minus, that is plus 0 0 and 0 minus minus for half duration of time. Okay. So, this is how VZS1 vector is formed. VZL1, this vector is formed by switching plus minus minus. VZL2 is formed by switching plus plus minus. Okay. VZS2 is formed by switching half of plus plus 0, this one, and 0 0 minus, this one, okay, half of. Now, the important part, VZM1, this vector, how are we generating this vector? We are generating by switching 1/3 of 0 minus minus, that is this one, plus 0 minus, that is this one, and plus plus 0, that is this one. Okay. So, by switching plus plus 0, plus 0 minus, and 0 minus minus for 1/3 durations of time, we get the VZM1 vector. Okay. So, now in our sector we do not have this vector. You can argue that okay, we are utilizing this vector, but we are not specifying that there is a vector here. Okay. Instead, we are saying that these black circles are our available vectors in this sector. So, we are redefining the space vectors in this sector. Okay. And what is our redefinition, or what is our new definition? The new definition is given by this. And how are we defining these vectors? We are defining these vectors by using these switching state combinations. The most important one is this vector VZM1, which is defined by saying that we will use these 3 vectors for 1/3 durations of time. Okay. So, this is the new definition. So, once we define these new vectors, therefore, what will happen? What will happen is we will have a new set of regions, okay, new set of regions in this sector. Okay. Earlier we had a different set of regions. If you see the conventional space vector diagram, if you see these were the regions, there were 4 triangular regions, okay, in this sector. But now with this new definition we will have 5 regions, okay. These are colored in this, and note that this is avoided. So, we have this region here 1, 2, 3, 4, 5. Okay. Before we go into the regions and how we switch, let us first see that how or why we have defined the vectors in this fashion. Okay. So, we have defined the vectors in this fashion. Let us see that after introducing this definition, what is the effect on the midpoint voltage, and that is what is interesting. So, let us see the effect on the midpoint voltage. Okay. So, again we assume that the TS period, switching period, is sufficiently small, so that all the currents are almost constant to their values. Okay. So, now let us see what will be the effect on the midpoint voltage. If we apply the VZ0 vector, then of course 0 0 0 and IA plus IB plus IC assumed to be 0, then the effect of the midpoint voltage is 0. If we use VZS1, as we have defined, VZS1 is defined as half of plus 0 0 and 0 minus minus, these 2 switching states combined, half of them, applying half of them, half of these switching states. So, in plus 0 0 we have seen that we have minus IA as the midpoint current, and with 0 minus minus we have plus IA as the midpoint current. So, if I apply this new vector VZS1, we will have a net current 0, okay, net current 0. Again VZL1, we know that when I apply plus 0 0, there is no effect on the midpoint voltage. When we apply VZL2, similarly there is no effect on the midpoint voltage, these two are large vectors. When we apply VZS2, that is this one, again we apply plus 0 and 0 0 minus for half durations of time, so as to create VZS2, and so its effect is again 0, half of minus IC plus IC and is equal to 0. We could have also said that T1 and T2 periods here, but anyway half of minus IC plus IC, and that is equal to 0. Now, you see the effect of VZM1. Now, you will see why VZM1 has been defined in this particular fashion. So, if you see VZM1, this vector, how have we defined it? We are switching 1/3 of 0 minus minus, this one, plus 0 minus, this one, and plus 0, this one, 1/3 of this. Now, what is the midpoint current with 0 minus minus? With 0 minus minus, the midpoint current is IA. With plus 0 minus, what is the midpoint current? IB. That was the problematic case. If you remember, this was the problematic case. IB was flowing out of the midpoint. And then with plus 0, what is the midpoint current? It is IC. So, if I apply VZM1 with this combination, the net current which we are taking out of the midpoint is again coming out to be 0. And so, again assuming that the currents are sufficiently constant in a switching cycle. So, therefore, we see that the application of VZM1, if we apply VZM1 or if we apply any of these vectors, then we will never cause any fluctuation or very small fluctuation on the midpoint voltage. Okay. So, now we are changing the space vector diagram by introducing additional vectors, and the most important one is the virtual vector VZM1. By introducing these additional vectors, what we are doing? We are ensuring that whenever we use these vectors, their effect on the midpoint voltage is 0 or minimum. Okay. So, the concept of this virtual space vector highly simplifies this problem, and it almost solves the problem. Now, this also you can see as compared to the first technique that we discussed, this technique can be applied at any modulation index, okay, because now the whole space vector has been redefined, whole space vector diagram has been redefined, and so this will be applicable for any modulation index. Okay. So, once we have redefined the space vector diagram with new virtual vectors, we have to also redefine the regions which are covering these space vectors. So, as I told you, we always, whatever may be the reference vector. So, if the reference vector is here, we will always switch the 3 nearest enclosing vectors, right. So, with the help in presence of these virtual vectors, now we are redefining the sector with 5 regions instead of 4 regions earlier. Okay. And what are these regions? You can see these boundaries of these regions are shown in the diagram. So, in region 1, for example, the enclosing vectors are, for region 1 here the enclosing vectors are Vz0, Vzs1, Vzs2 like this. For region 2, the enclosing vectors are Vzs1, Vzm1 and Vzs2 like this. For region 3, these are the 3 enclosing vectors. For region 4 these are the 3 enclosing vectors, and for region 5 these are the 3 enclosing space vectors, okay. And this is shown here. So, when the reference vector is here, we will, for example, if the reference vector is here, we will switch. So, it is in region 5, we will switch V z m 1, V z L 2 and V z S 2. Okay. Now, again the same principle of volt second balance we will apply here also. Okay. So, we will see that by applying volt second balance we can be able to realize the reference vector. Okay. Now, one question that will automatically come up now in your mind is that this V z m 1 is a combination of 3 vectors. Okay. V z m 1 is not a vector which is obtained from a direct switching. V z m 1 is obtained by switching of 1/3 of these 3 vectors here. So, will it not increase the switching frequency? Yes, indeed it will be increasing the switching frequency, and that is correct. By use of this V z m 1, the switching frequency in fact increases by about 33%. However, the midpoint voltage fluctuation has or is highly minimized with this technique. Okay. So, we can see how the modified switching will look like with this kind of a virtual vector. How will it look like? So, with conventional switching, reference vector is somewhere in here. Okay. Suppose the reference vector is here. Okay. So, we will now see or compare how much will be the extra switching due to the virtual vector. Okay. What happens in a conventional space vector PWM for NPC, and what happens when we introduce this virtual vector. If we had used conventional switching to realize this vector, what we would have done? We would have done this for this one, you would have done say plus 0 0 plus 0 0 and plus 0 minus plus 0 minus, then going to 0 0 minus this one, and again coming back to 0 minus minus. So, for realizing this reference vector in conventional switching, we would have used these 3 vectors with such a switching sequence, and in this switching sequence every time there is one change of or one transition of change. So, plus 0 0 to plus 0 minus means C phase is changing from 0 to minus. Okay. Now, let us see what happens with the use of the V z m 1, how can we make a modified switching. So, in order to fully understand the V z m 1, what we will do here, you see this is kind of a slightly advanced PWM technique, but I introduce this to you because you see what are the possibilities with PWM. So, with advanced PWM many possibilities open up, and so I would like you to introduce you to these advanced, slightly advanced PWM techniques. So, when the reference vector is here in this place, then what happens? See, we define that okay, V z s 1 is switched for T1 duration. Okay. So, this one is switched for T1 duration, V z m 1 is switched for T0 duration, and V z s 2 is switched for T2 duration. So, that we know that T1 plus T2 plus Ts. So, T1 plus T2 plus T0 is equal to Ts, the total time period. Now, what we do before I switch the V z m 1, first I will divide this T1 into two parts, T1 by 2 and T1 by 2, T0 into three parts, T0 by 3, T0 by 3, T0 by 3, and T2 into two parts, T2 by 2 and T2 by 2. So, I am splitting the timing duration and we will apply the vectors, space vectors in a clever fashion. But first we have split the timing durations into several such subparts. So, T1 is split into T1 and T1 by 2 and T1 by 2, T0 is split into T0 by 3, T0 by 3, T0 by 3, and T2 is split into T2 by 2 and T2 by 2. Fine. Next, how am I going to apply the vectors? So, we will now place these timings in a different fashion, not in this sequence. Okay. So, you see how we are going to place the timings first. So, this T1 by 2 comes here, but then I have a T0 by 3 time which I go from here to here. Then I put a T2 by 2 timing here. Then I put another T0 by 3 here, then T1 by 2 here, T0 by 3 here and another T2 by 2 here. So, you see that in a switching cycle, placing of these vectors can be done, like the timings can be interchanged. Of course, this will create a poorer harmonic performance. We understand that it will create a poorer harmonic performance. However, if the switching frequency is sufficiently high, which is most of the case applicable, then this poorer harmonic performance may be acceptable. Okay, it should not be any problem, because if the Fs, or because in this case the harmonics will reside at 2 Fs. So, in that 2 Fs we can filter it out, the harmonics. So, but now what we are doing, we are redistributing these time periods in a different fashion. Okay. Now, what we are doing, in this T1 by 2 period I will apply Vz_S1 vector. In this T0 by 3 period I will apply Vz_M1. In the T2 by 2 period I will apply Vz_S2, and similarly Vz_M1, Vz_S1, Vz_M1 and Vz_S2 corresponding to this table here. Okay. Corresponding to this table I will apply the vectors here. Now, so if you remember, I told you that Vz_S1 was half of 0 minus minus and plus 0 0. If you remember, Vz_S1 was half of plus 0 0 and 0 minus minus. So, this 0 minus minus and plus 0 0 are here, okay, that half. So, this is half of 0 minus minus and half of plus 0 0. Okay. So, these two are here. Similarly, Vz_M1 was 1/3 of 0 minus minus, plus 0 minus and plus plus 0, 1/3 of 0 minus minus, plus 0 minus and plus plus 0. So, 0 minus, so this is 1/3, 1/3, 1/3 here. Okay. And Vz_S2 was half of 0 0 minus and plus plus 0, these two half of. So, this is how this is done. Okay. So, if you do like this, if you place your switchings like this, what happens with the changes? From here to here you see there is no change, there is no switching change, identical. From 0 minus minus to 0 0 minus you have one change. From plus 0 minus, so from this to this you have one change. 0 0 minus to plus 0 minus means you have the plus changing from 0. So, one change, and then from here to here you have one change, from here to here you have another change, and for the last one there is no change. So, therefore, you see that there are 4 changes happening in a TS period by using this strategy of virtual space vectors. Okay. So, there has been 4 switching transitions, which if I had used the earlier one, there were 3 transitions. If I had used this one, there were 3 transitions, but now we have 4 transitions. Okay. And so, we have about 33% more switching losses with this technique. Okay. However, the advantage is that we are now able to minimize the midpoint voltage fluctuations. Okay. And this also shows that how we can play around with the vectors and the placement of the vectors in a switching cycle TS. Okay. You can place these vectors in different ways. Okay. You can also make the vectors one sided, like discontinuous PWM. So, you can make the T0 vector T0, T1, T2, you can make T0 by k or k times T0 and 1 minus k times T0, and then T1 and T2, you can make k 0, you can make k other values. So, in that way you can play around with the vectors and their timing durations, and one way of doing is shown here. Okay. And in this way it is possible to do many things, and one of them is like midpoint voltage fluctuation minimization.